Welcome to this course devoted to concentration of measure. First of all, I would like to give you a roadmap. I shall give you 7 lectures that will end in November. The conditions of the exam will depend on the evolution of the COVID crisis, but it could be a classical form, that is several exercises to solve during 3 hours. It is at least classical in the French system. Otherwise, I shall adapt. I am providing some notes, which are extracted from a book that I have written with my colleagues, Stéphane Boucheron and Gabor Lugosi. And this book is entitled Concentration Inequalities, Another Synthetic Theory of Independence. I shall quite stick to the book. Maybe the introduction will be a bit different of what it is in the book. It will be a bit different, but concerning the second chapter on basic inequalities, the chapter devoted to the control of the variance of functions of independent variables, and also the chapter devoted to information theory and log-sum inequality and the entropy method. I shall really stick to the book. After that, I shall give you some more advanced material on transplantation methods. As you will see, it's a very beautiful way of looking at concentration. And I shall end the lectures by considerations about phi entropies and moment inequalities, which, as I have mentioned, are a bit more advanced material. So, what are we talking about? Let's begin with very classical probability theory. Let us consider some IID, real-valued random variables that we assume to be centered at expectation. And let us focus on the behavior of the sum of these variables. Everybody knows, of course, that if I divide this sum by n, the law of large numbers ensures that it tends to 0 almost surely, and also in probability, of course. And if the random variables are known to be square integrable, let us standardize them. Let us assume that the variance is equal to 1. Then the central limit theorem tells you that Sn over root n converges to a standard normal distribution. So this means that if we look at the probability that Sn over n is larger than epsilon, that is the right tail of the random variable Sn over n, then this tail has a different behavior depending on the size of epsilon with respect to n. If epsilon is given, this is the law of large numbers regime, and the tail probability tends to 0 when n goes to infinity. But if theta is given, and if epsilon is chosen equal to theta over root n, then you are in the CLT regime, and this means that the same tail probability as before converges this time to the Gaussian tail. So this means that from a probabilistic point of view, what measure concentration will provide us is non-asymptotic informations about the tail probability. That is, informations that do not depend on the size of epsilon. So this will be the main novelty with measure concentration methods here. So I would like to focus a little bit on the Gaussian tail in order that everybody knows exactly what we are talking about when we talk about the size of the Gaussian tail. So if you look at the Gaussian tail, it is quite well known that the equivalence when theta tends to infinity of this Gaussian tail is something like 1 over square root of 2 pi times theta times some exponential of minus theta square over 2. And it is also a classical exercise to show that the Gaussian tail is smaller than 1/2 times exponential of minus theta square over 2. So what have these two results in common is that you make appear the same quantity here, the same exponential decay, but you have two different things here which appear. So this means that if you multiply the Gaussian tail by exponential of theta square over 2, this quantity behaves in the following way. Its maximum is 1/2, and it decreases like 1 over square root of 2 pi theta when theta is large. This is the meaning of the two results here. So to get the first result, the equivalence result, then it's quite easy to do that. You integrate by parts. You just interpret the initial quantity as a product of there's two quantities here. You integrate this part and you derive this part here. And so you get this identity, and the integrated part of this integration by parts will give you an upper bound for this integral here, since there you have this minus sign, which tells you that the quantity which is here is non-positive. So we have this as an upper bound. If you iterate this procedure, if you integrate by parts one more time, then what you get is that you have this integral which lies between this quantity here and this one. And of course, since when theta tends to infinity, there's two quantities are equivalent here, you get as a result the fact that this integral is equivalent to 1 over theta exponential of minus theta square over 2. And this gives you the announced result. Now, concerning the exercise, the hint is that you have to study the tail of the Gaussian tail times 2 times exponential of theta square over 2, and check that the function here has its maximum, which is achieved at theta equal to 0, and that's all. So now I would like to turn to a very, very beautiful result, which is in some sense a benchmark in the theory of concentration. And this is the Gaussian concentration theorem. So this theorem has two different aspects. I begin with the geometrical aspect because this is something very new for you, and this will make you realize that there is something new which will happen if you look at this new theory. There is something new with respect to what you know in probability theory. Okay, so this is the Gaussian isoperimetric theorem, which is due to Christer Borel. You are just considering IID standard normal variables. And so the vector, the random vector with coordinates corresponding to these variables. So you get a standard Gaussian random vector in the Euclidean space Rn. For any theta in 0, 1, if you look at the probability that x belongs to the T neighborhood of the set A, then this probability is minimal when you consider a half space if you have fixed the probability that x belongs to the sets A. And of course, since the half spaces have all the same probability in some sense under the Gaussian distribution, because it is invariant by rotation, then you can fix the half space to this shape here. And if the half space has this shape, the constraints that the probability that x belongs to the half space is equal to theta just means that the Gaussian tail at t theta has to be equal to theta. So this is a beautiful isoperimetric theorem, and it has the following consequence. Since the number t theta has to be non-negative when theta is larger than 1/2, if you consider some set with probability larger than 1/2, then the probability that the distance from x to A is larger than t has to be smaller than the Gaussian tail at point t plus t theta. This is a consequence of the preceding theorem. But since t theta is non-negative, this tail is also less than the Gaussian tail at point t, which is also less than exponential minus t squared over 2. Now, what happens if we look at Lipschitz functions? For the moment, we have a consequence on the distance function from x to any set A with probability larger than 1/2. And we would like to commute this result on a concentration result for a function, which is Lipschitz, of the random vector x. So this is very easy, in fact. If you look at one Lipschitz function, you apply the preceding inequality to the set for which the function is less than a median. So if you look at a median of the random variable z equal to f of x, then the probability that z minus the median is larger than t will be smaller than exponential minus t squared over 2, exactly because you can use this inequality here. Okay? So what is nice is that the same inequality holds true for the expectation instead of the median, which for the application is very good news because it's often easier to work with the expectation. But the proof will follow a very different path, as we shall see later on. And meanwhile, as you can see here, the Gaussian tail is the standard Gaussian tail. So you have the Gaussian tail for the variance equal to 1. And so it is not surprising to see that meanwhile, the variance of z is also controlled, and it is controlled by 1. This is what we shall call a Poincaré type inequality. And in order to just see what is the power of this result, just think about the easy example where you consider as a Lifshitz function the Euclidean norm itself. In this case, the variable z square follows a chi-square distribution with degree equal to n, and so we can compute explicitly this expectation of z square, which is equal to n. So this means that the preceding inequality on the variance exactly means that the expectation of z square is switched between n, which is exactly the expectation of z square, and n minus 1. So you see that this inequality is very sharp, and in some sense, it is some kind of converse here. This inequality is a converse of this one, which is merely Jensen's inequality. So you see that in this case, the concentration result, which is the control on the variance here, provides you some sharp converse of Jensen's inequality. What is the case of equality in Jensen's inequality? The case of equality is when the variable is constant. So when you see that Jensen's inequality is sharp, this means that you have a variable which is almost constant. So the message here is that a one Lifshitz function of many standard Gaussian random variables is almost constant. And now, all along these lectures, what we shall try to do is to extend this result to function of independent random variables in general. And we shall look at concentration inequalities of these functions around their expectations. The kind of inequalities that we shall look at are sub-Gaussian inequalities. Of course, in the general case, you cannot expect such as neat inequalities as in the Gaussian case, but as you will see, we shall get some sharp results where we shall be able to provide a Gaussian decay here for the tail probability with a variance factor which will be typically a good upper bound for the variance. And here, some bandwidth in which this inequality holds true, with an upper extremity for this bandwidth, which is x null here, and which is explicit. And sometimes it will be equal to plus infinity in very favorable cases. But in general, it will be something which is explicit and as large as possible. So this is the kind of result that we shall try to prove. When you have a Gaussian variable, but it's a bit too ambitious to find the variance here, but a good upper bound of the variance will be okay. And now we hope that this inequality will hold on the full half line, 0 plus infinity, but again, it will not be the case, generally speaking, and more generally, we shall be able to prove inequalities which are sub-Gaussian, but in the bandwidth. And of course, we expect this the end of the bandwidth here, the supreme of the bandwidth, x null, to be as large as possible. But we shall leave that it is an explicit value. Okay, so this is the kind of result that we shall try to prove. So now you can ask me, but why are we so interested by functions of independent variables? The reason is that functions of independent variables, you find them appear in many examples coming from probability theory, coming from combinatorics, statistical mechanics, statistics, machine learning. Many branches, in fact, of mathematics make functions of independent variables appear. So I shall try to give you some examples. And I begin with the easiest one, which looks like the sums of independent and real valued random variable we started with, but with a slightly different context, which will make the difference. So let's talk about probability in Banach spaces. Instead of looking at real valued random variables, we are looking at independent independent variables with values in a Banach space, a separable Banach space. So you look at the sum, exactly as we did with real valued random variables. And we will be interested this time by the concentration of the quantity, which is simply the norm of the sum. So the norm of the sum, if you want to look at it as a function of random variables, which where you will see the link of real valued random variables, this is easy. You just have it to interpret the norm as the soup over the unit ball of the dual of the Banach of linear forms. Okay, so this is what I am doing here. The norm of the sum, you simply write that it is the soup over the unit ball of the dual of the Banach space of the sum of real valued random variables, which are simply the quantities, so T of xi here. So you will see that you have some of real valued random variables which appear here, but you have also this supremum, which makes some nonlinearity appear, and which makes appear a new difficulty as respect to the study of some of real valued random variables. So this is makes this quantity more difficult to handle than the usual sum of real valued random variable. But of course, you need some kind of regularity here because you keep convexity. So let us consider some generalization of this example here, when this time we shall look at the same kind of quantities, but losing the linearity of T with respect to xi. So this is what we are looking at when you are looking at empirical processes here. So this is the same kind of object in some sense, but here you consider any measurable function gt of xi instead of looking at linear functionals on the Banach space. So here you have a generalization of the preceding example. And of course, you have to assume here, in order to avoid measurability disagreements, that you are looking at a set T which is finite or countable. But this is an example which is important because it appears to be an example which is interesting for statistics here. So let's see an example which comes from another universe. We are looking at discrete random variables which are meaningful in random combinatorics. So you simply consider a family of 0,1 valued random variables, which are IID, and you look at what people call a Boolean polynomial with degree D. That is that you are looking at products of the variable xi with a number of xi ending in the products, appearing in the products here, which is equal to D. And then you sum over all the possible sets with cardinality D in the family I here, calligraphic I. So this has a random graph interpretation. So what is a random graph? This is the Erdős-Rényi model. You are simply connecting two vertices if you have a draw of a Bernoulli variable which leads to a success. Okay, so you connect A and B if the random variable that you have drawn, which is a Bernoulli, is equal to 1. And you do this for all pairs of vertices independently. So this gives you variables which are IID and with values in 0, 1. And you can ask yourself, what is the interpretation of a Boolean polynomial in this case? And in this case, it simply represents the number of complete subgraphs of this random graphs with length D. So let's see what it gives for D equal to 3. Here is a random graph. And you see here that the number of triangles in yellow here is simply equal to 3 on my example. Okay, so for D equal to 3, you are simply counting the number of triangles in the random graph. So this quantity, of course, is non-linear. It's far from being a quantity which looks like a sum of independent variables, but nevertheless, you want to give some information, to get some information on the behavior of this quantity. So another example which comes from random combinatorics is bin packing. So what are we doing with bin packing? We are considering independent and identically distributed random variables with values in the segment 0, 1. And you are considering coverings of 0, 1 by disjoint intervals, but you only consider the coverings that respect some kind of budget that you have. And this budget is simply that you want to warrant that the sum of the variables here is less than 1. So this means that you have a collection of coverings which is admissible. That is, you are respecting this constraint here. You are respecting your budget. And you are interested in the behavior of the minimum length of admissible coverings. Okay, so you are, in some sense, looking at the optimal coverings, that is the smallest one, which are respecting your budget. So another example, which is quite famous, is that you want to analyze the longest increasing subsequence. So you consider exactly the same framework as in the preceding example. That is, you are looking at IID uniform variables, and you say that the subsequence is increasing if the variables are ordered in the same way as the indices. Okay, and you are looking simply as the longest increasing subsequences, that is the quantity which is the maximum of increasing subsequences. So this quantity is again far from being linear, far from being close to a sum of random variables, but anyway, this is a function of independent variables, and you would like to get some information about its behavior. So the last example that I shall give comes from the theory of random matrices. There are several interesting problems to look at from the concentration point of view on random matrices, but here is one. So what are we looking at? We are looking at symmetric random matrices. So the independent variables are simply a triangle array, and you replicate this triangle array above the diagonal in order to get a symmetric random matrix. And one of the issues that you would like to look at is simply the behavior of the largest eigenvalue of this random matrix. And you see that this larger eigenvalue, you can express it, of course, as a supremum over the unit sphere, the Euclidean unit sphere, of U transpose AU. So you see here that you again make appear a supremum over something, but for a quantity which is no longer linear with respect to U, but which is quadratic. So again, you would like to get some information on this quantity here. So all along the lectures, we shall come back to these examples and see what the techniques that you shall develop will give on these examples. And you can find, of course, many more examples in the notes. So now I turn to the mathematical basics. What kind of mathematics shall we use to tackle this problem? So first of all, I will give you good news. That is, you can forget about all what you know and just focus on what I shall tell you from right now, because I shall give you an exhaustive view of the theory. That is, I shall prove everything that I shall announce in some sense. Okay, so you can start from zero and just try to understand what I'm talking about. So starting from zero maybe is not exactly true. We start from something which is very elementary here, but which is very important in probability, that is Markov's inequality. So the basics in some sense is Markov inequality. So you start from Markov inequality, and as you know, a simple way of using Markov inequality is to use it for the square of a centered variable, and this leads to Chebyshev's inequality. And what makes the square attractive, you could use another power than the square to use the Markov's inequality. What makes the square attractive is that you have an additive formula, which is very, very convenient, it's very pleasant for in the case where the sum is, where the variable at hand, is simply the sum of independent variables. You have this very nice additive formula. So first of all, the first remark that I would like to make is that, of course, this is the case when you look at the sum of random variables. But when you look at some function of independent variables, which is not a sum, then it's already a challenge to prove a good bound on the variance. So this will be one of the purpose of these lectures, to develop strategies to provide good bounds on the variance of a function of independent variables. So I'm doing what I have promised, that is Markov inequality, though it is very elementary, I prove it. I recall you what is Markov inequality. So this is very simple. Of course, you look at some non-negative random variable, and you just say that when this variable is larger than t, it is larger than t. That is, this variable is greater than t. So on this set here, on this event here, y times the indicator of y larger than t is larger than t times the same indicator. So when you take expectation on each side, then you get an upper bound on the probability of the tail, which is simply the expectation of y over t. You could have kept this guy here. Sometimes it's useful because it's tending to 0 when t tends to infinity. But when you want to get an asymptotic upper bound, in some sense, it's good to look at this quantity here, which is simply Markov's inequality. Okay, so as we shall see during the lectures, additivity is a very, very special case, but subadditivity will be the key to address the general problem of understanding the behavior of functions of independent variables. So there is another situation where you can make additivity comes in. Instead of looking at the square as a transformation of the variables before using Markov's inequality, you can use the exponential. So this is very interesting because when you use an exponential transformation, then you have some parameter lambda, which appears because when you look at an exponential transform, you can use a parameter. And so this means that when you use this transform, you have in the one hand that again you have additivity, just because of the well-known fact that the exponential of a product is a product of just because of independence, and then after that the use of the properties of the exponential and the log. Okay, so you have again additivity, as in the case of the square. And you can use this time this additivity through the Markov inequality and optimize over the parameter lambda and get something which is historically very important, that is at the basis of the large deviation theory. And the first result in this direction is Kramers Theorem that we shall prove during the introduction of the lectures. So we shall prove it in a moment. So before proving Kramers Theorem, let's see what gives you the optimization with respect to the parameter lambda of Markov inequality. And it is very simple. You write that the probability that y is larger than x is also the probability that the exponential of lambda y is greater than the exponential of lambda x when you take a positive value of lambda. And it is less, of course, than the exponential of psi y of lambda, which is simply this quantity here, times exponential of minus lambda x. And of course, this is true for all values of lambda. And so lambda is a free parameter, and you can optimize the inequality that you've got above. You can optimize it over all possible values of lambda. And this leads you to what is called Chernov's inequality. And Chernov's inequality, you can rewrite it in a slightly different way by using the theory of duality for convex function. And it goes as follows. The dual of a convex function, in the sense of Legendre, is simply this quantity here. This is the dual. Okay? And this dual is a bit different than the quantity which appears in Chernov's inequality, just because above you have this constraint on lambda, which is that lambda is non-negative. But in the definition of the dual, lambda is completely free, and you look at the soup on the whole real line. So the first remark that we shall make is that, I just come back to the issue of convexity. As I mentioned, I am proving everything. The convexity of the log of the moment generating function is simply a consequence of Hölder's inequality. So you write Hölder's inequality and you just take the log. When you take the log on each side of Hölder's inequality, then you get directly that the function psi I is convex. And of course, you also get that the set lambda over which this transform is finite is an interval. Because of course, it's not obvious at all that when you look at the moment generating function, it is a finite quantity. For some lambdas, it may be finite. For some others, it may be infinite. And of course, if it is finite on a non-trivial interval, it is always finite at 0, it is equal to 1. But when it is finite on a non-trivial interval, this means that you have a variable which is very integrable. All the powers are integrable. So this is not obvious at all that the quantity the moment generating function, excuse me, is finite on a non-trivial interval. But when it is the case, nevertheless, the set where it is finite is an interval. So now we can rewrite Chernov's inequality, as I have announced, in a slightly different way, just because we can analyze closely where the supremum of the is achieved. So the lemma tells you the following thing. If you have a random variable, if you look at x, which is larger than the expectation, then the dual is equal to the sup over lambda, which is non-negative, of lambda x minus psi y of lambda. In other words, the sup which defines the dual here is achieved on the for non-negative values of lambda. It is what this lemma says. So let's go to the proof. The proof is absolutely trivial. At 0, we know that the quantity here is equal to 0, which means that the sup is at least non-negative. Okay? And so what you look at, what happens for a negative value of lambda, Jensen's inequality ensures first that psi y of lambda is always greater than lambda times the expectation of lambda. And this means that lambda x minus psi y is always smaller than lambda times x minus the expectation. X minus the expectation is non-negative because x is larger than the expectation. And if lambda itself is negative, this means that its quantity is negative. And so the sup cannot be, the sup is achieved, excuse me, for non-negative values. Okay, it cannot be achieved on the negative part. Okay, so this is the proof. And the consequence of this is that you can rewrite simply the Chernoff inequality in the following way. If you look at a non-negative value of x, then the log of the probability that z minus expectation is larger than x is smaller than minus this dual function in the sense of Legendre. Okay, so in the theory of large deviation, people are often talking of this quantity as being the rate function. Okay, because it gives you the rate of the exponential decay of the tail probability. So you can compute this quantity explicitly. So it's not surprising to see that in the Gaussian case, you make appear what you expect. That is, if you have a centered normal with variance v, then this rate function is simply x squared over 2v. And if you have a Poisson distribution, it's interesting to make the computation. You have another function which appears, and this function, we shall see it appear several times. That is 1 plus t log of 1 plus t minus t. Okay, so here you have the duality square versus square. When you start from a square, you take the dual, it is a square. And here you have another duality, it's exponential versus log. Okay. So in the case of the normal distribution, I do the computation in order that you see how to compute a dual function. It is very simple. You look at the supremum of this quantity here, you derive with respect to lambda, and you find that the maximum is achieved at the point where the derivative is equal to 0, that is the point lambda x, which is such that lambda x times v is equal to x. And therefore, the value of the dual is lambda x times x minus the moment generative function of the normal, and you compute the value, which is minus this quantity, and you have plus this quantity here, and you end up with x squared over 2v as announced. So this is very simple. You should make this calculation by yourself in order to convince yourself that it is very elementary. So now I turn to large deviations. So it's something which is not completely essential to understand concentration, but it is important to realize that the rate function is really something which is sharp. That is, in the simplest case ever, that is the sum of independent random variables, you can see that this rate function captures the exponential decay of the tails. This is the idea of large deviations. So the natural question is Chernoff inequality optimal? In the Gaussian case, we lose something which is a half uniformly, or 1 over theta times 1 over root of 2 pi, if you look at what happens when theta is large. So essentially, what you see in the Gaussian case is that the exponential minus theta square over 2 is the right quantity to look at. But in front of this quantity, you don't know exactly what should appear. So in some sense, the large deviation regime will ignore the small polynomials that appear in front of the exponential decays. It will look at the behavior of the log probabilities. This is the idea. And Kramers Theorem will tell you that the rate function is optimal, and it is the right quantity to look at in order to capture the exponential decays of the tails. So let's see exactly what is the statement of Kramers Theorem. We look at independent and identically distributed random variables with values on the real line, and we assume that they are centered at expectation. And we assume that they are integrable and nothing else for the moment. And we consider their sums. And we shall write psi for short to denote the log of the moment generating function of a single variable here, x1. So the statement of Kramers Theorem is very simple. For all non-negative values of x, the limit of 1 over n of the log of the probability that Sn over n is larger than x is equal to minus psi star of x. Psi star is the dual of psi. And in the similarly, for negative values of x, you have the same result on the left tails, okay? So of course, it's enough to consider the proof of the right tail, because changing the variables into their opposites, if you have the result of the right tail, you have the result on the left tail. Okay, so just focus on the right tails. Okay. Now let's look at the easy part of the Kramers theorem, which is simply to use Chandler's inequality. So to use Chandler's inequality, we again use the additivity of the log of the moment generating function. So the log of the moment generating function of the sum is equal to n times psi. So for the dual, this means that the dual of Sn over n is simply n times the dual of psi. And you use Chandler's inequality in order to derive that 1 over n, the log of the probability, is smaller than minus psi star of x. So this means that in the statement of Kramers theorem, this statement tells you that the limit is equal to something, and you discover that talking about the upper bound, because of course, to show that the limit is equal to something, we shall prove that the lim sup is smaller than something and the lim inf is greater than something, okay? And talking about the upper bound on the lim sup, in fact, it is non-asymptotic, that is, it is true for all values of n. So of course, this implies that the lim sup is smaller than blah, blah, okay? But it's much stronger in some sense. It holds whatever the value of n. But the lower bound is asymptotic. That is, to prove the lower bound, what we shall prove, in fact, is something which looks like a stronger result, but it captures the essence of the large deviations. It tells you that whatever the value delta that you consider here, if you look at the log of the probability that Sn over n belongs to this small interval, if you look at the 1 over n times this log, the lim inf is larger than minus psi star of x. So this means that the quantity minus psi star of x is optimal, of course, and this is the meaning of Kramers theorem. So to prove that, we need an idea. So the upper bound, okay, it's easy. The lower bound, this is something which is more subtle, and which to prove it, you need really some idea. So why is it subtle? It is subtle because when you look at Sn over n, its expectation is equal to 0. So what we have in mind is that Sn over n has values which are concentrated around 0. And you want to look at the probability that Sn over n belongs to some interval which is far from 0, which is x plus delta. And x is far from 0. So this is not easy, this is not obvious. So how we can do that? We need an idea. And the idea of Kramers is to use a change of probability distribution. Is to use a change of probability distribution in order to put the mass around x instead of around 0. In order to have a distribution that makes the Sn over n concentrates around x instead of around 0. That's a very, very beautiful idea. I love it. Okay? So let's see how it works on a very simple example. That is, we just take a single variable. After that, of course, we shall make this transformation, this change of probability on a product situation. But here we consider just a single variable with distribution mu. And we just introduce the exponential change, which is this one. That is, you multiply the probability P by some exponential quantity, which is exponential of lambda x, x is a variable, times the exponential of minus psi of lambda, of course, in order to get a density, in order that this quantity has an integral on the P, which is equal to 1, okay? And what is magic is that under this new probability, the expectation that you compute here, the expectation is what? It is the expectation under P of the quantity multiplied by the density. So this is what you get here. And you see that this quantity can also be interpreted as the derivative of psi. Okay? But if you choose lambda in a subtle way, that is, you choose the very value of lambda, which is such that psi prime of lambda x is equal to x, then the expectation will become equal to x. This is exactly what you need and what you want. You want the expectation to be equal to x instead of 0. Okay? That's one point. And the other important point is that this very value where psi prime is equal to x is also the value where the function which allows to define the dual achieves its maximum. So this means that you have now the right idea and you have to make it work in order to prove the low bound and the Kramers theorem. This is a good point to make a good moment to make a break. So we make a 5-minute break and start again in 5 minutes, okay? So I'm starting the recording of the lecture and I will restart afterwards, okay? So we take a break. Exactly at point X, or if there isn't, okay? So the first assumption that we make is that we have an ordinary point for the measure, that is, there is some life after point X. And after that, of course, as I mentioned to you, we shall relax these two assumptions, but for the moment, we make these two assumptions here. So the first step of the proof is to show that the function lambda gives lambda x minus psi of lambda achieves a maximum at some point lambda x, which will be non-negative, because we know that when x is non-negative, the maximum has to be achieved at some non-negative point. Okay, so let's see what happens. The function psi of lambda is always larger than the log of the integral starting from x plus eta going to plus infinity of exponential of lambda t d mu of t. the function psi lambda is equal to the log of the same integral starting from minus infinity. But of course, if you restrict to x plus theta plus infinity, you have a lower bound. So when you look at a non-negative value of lambda, and this means that psi of lambda will be larger than what? If you take some non-negative value of lambda, if t is larger than x plus eta, of course, exponential of lambda t will be larger than exponential of lambda x plus eta. Okay, so we can say that the log of the integral will be larger than the log of the value of the function at this point here, that is lambda times x plus eta. And then the integral will be larger, so the value of the function at this point times the measure of the interval. And so when you take the log, this gives plus the log of the measure of x plus eta plus infinity, which is what it is, okay? But which is not infinite, because we know that the measure of this interval is positive, okay? Okay. So when you go now to the function of interest, that is lambda x minus psi of lambda, it is less this time that lambda x minus lambda x plus eta minus the log of the measure of the interval x plus eta plus infinity. And of course, there's two quantities here cancel, and you end up with an upper bound, which is minus lambda times eta minus log. And of course, this goes to minus infinity when lambda goes to plus infinity. And so what is happening here? Of course, the function lambda gives lambda x minus psi of lambda is perfectly continuous. It is even infinitely differentiable. Since we know that the support of the measure is compact, we have no problem to consider this function on any value of lambda, it is regular, so this is not a problem. So we have a continuous function which is equal to 0 when lambda is equal to 0, and which goes to minus infinity at plus infinity. So this means that this function behaves like that. You have something like that. So it achieves the maximum at some point, lambda x. I don't pretend that it is unique, because it could be flat here. Why not? Okay. But at least it has a maximum. Okay. So there is some point lambda x at which the function lambda gives lambda x minus lambda achieves its maximum. And of course, at this point, the derivative has to be equal to 0, which means that psi prime of lambda x is equal to x. It is exactly what we had in mind. So now we can change the distribution. But this time we have to do that on the product space, because we don't have a single variable. We have the set of independent variables, x1, xn. So the easiest way to do that is to have in mind that we are working on the canonical space. That is the space where the probability P is equal to mu to the power n. Okay, this is the easiest situation. This also means that the probability space is Rn. Okay. So on a single variable, the change of distribution becomes something which is related to the distribution mu. That is, we consider d mu x of t, which is exponential lambda x times t over exponential of psi of lambda x du. Of course, this quantity here is such that the integral with respect to mu is equal to 1. This is exactly the normalization which makes it the density. So as announced, we have a mean for this new probability distribution, which is equal to psi prime of lambda x, and it is equal to x. This is what we have seen just before starting the proof of Kramers theorem. Okay. And now, if we consider the random variables x1, xn, which are simply the projections on Rn, our probability space is Rn, and we consider the change of probability mu x to the power n. This is the change of probability. Each variable xi is such that the expectation of xi under this new distribution is equal to xi. Because all these guys are independent with the same distribution, mu sub x. Now, what is the density of this change of probability? The density is easy to compute. This is simply, so if you look at that density of mu x to the power n over mu to the power n, if I compute it at some points x1, xn, is just the product of the individual densities, that is exponential of minus n psi of lambda x times the exponential of the sum of the xi. So now, if we look at the probability of interest, which is the probability that Sn over n belongs to the interval x plus eta, this is equal to what? This is equal to the expectation of exponential under x, excuse me, of exponential of minus lambda x times Sn times the indicator of Sn belonging to x plus eta and times the exponential of n psi of lambda x. Okay, so this is very simple. I want to express this probability which is computed under the original distribution. So remember that P is nothing more than mu to the power n. And I make the change of probability in the reverse sense. That is, I express that this probability is equal to the expectation of the indicator set times 1 over this density here. That is exponential of n psi of lambda x times the exponential of minus lambda x Sn. Excuse me, there is some x missing here. Okay. Okay. And so now we do exactly the same kind of thing as in Markov's inequality, but in the reverse sense, I would say. And we notice that on the event, which is Sn over n belongs to x plus eta, we know, of course, that Sn is smaller than n times x plus eta. So what is important here is that since this quantity Sn is smaller than that guy, the exponential of minus Sn lambda x will be larger than exponential minus lambda x times this quantity here. Okay, so this means that this is the probability we started from, that is the probability that Sn over n belongs to x plus eta is larger than the exponential of minus lambda x times n times x plus eta. So let's see. This guy here has a sun. Its sun is this guy here, okay? Because we know that Sn on this event is smaller than n times x plus eta, and so I plug this maximal value here, okay? So I get this plus n times psi of lambda x, which was already there, n times the expectation of an indicator set, that is the probability under x of Sn over n belonging to x plus eta. So let's see. Let's summarize what we have. The probability that then Sn over n belong to x plus eta is lower bounded by what? It is lower bounded by exponential of minus lambda x and minus n psi of lambda x plus n of times psi of lambda x, excuse me, minus lambda x and eta, and times the px probability, which is up there. So things are becoming very pleasant here because we know that lambda x there is an x missing. We know that lambda x minus psi of lambda x is exactly equal to psi star of x. Great. And so what we see here is that if we normalize everybody by 1 over n, and we take the log of the probability, this is what we have to look at. At this scale here, what we get is simply minus psi star of x, and we are happy. We have an extra term which is minus eta times lambda x. The n factor has been destroyed by the 1 over here, and here it has been cancelled. And so we are not happy with this guy, but there is no problem with it because eta is as small as we want, so no problem. And we have a last term, which is plus 1 over n, the log of the px probability that Sn over n belongs to the interval x plus eta. And so we have to do something with this guy. If we can show that this tends to 0 as n goes to infinity, we shall be happy. And the proof will be finished. But we have to prove that this guy tends to 0 as n goes to infinity. Well, that's not that easy. but we have to think quietly to the behavior of this quantity. So let's see it. Let's focus on it. Let's forget for the moment the 1 over n log. Just to look at this quantity here. What can we say? This is the very moment where we have to realize that we have done exactly what we had to do in order that this guy here is not degenerate. Why? Because we know that the variables here are centered at point x. So this means that I can rewrite this quantity, if I wish, as the probability that Sn minus n times x 1 over root n belongs to the interval 0 times eta root n. I can rewrite it this way, okay? And what is the behavior of Sn minus n times x over root n? The variables are bounded, they are moments of any order. So we know that the CLT applies, and we know that Sn minus n times x over root n over some quantity sigma, which is the square root of the variance of the variables, converges in distribution to a standard normal. Okay, so this means that when we look at the behavior of px of Sn minus n times x over root n to be larger than y over sigma, this tends to the distribution function of the standard normal at point y. And you may know that this convergence is uniform with respect to y. This is due to the fact that there's a distribution functions here are monotone. They go to some continuous limit, and it's exactly as in the theorem like Dini's theorem. This convergence, excuse me, has to be uniform. So you could object that we are not on a compact set. We are on the values of y which goes from minus infinity to plus infinity, but in fact it works because the limits when y tends to plus infinity and minus infinity of these guys are the same. It is +1, it is -1, and so it is exactly, believe me, the same kind of proof that you know with Dini's theorem, and so the convergence is uniform. Okay. So if you accept that, this means that you can do some things that you are not allowed to do if the convergence is not uniform, but if it is uniform, you can do it. You can plug a value of y which depends on n. That is eta times the square root of n, and make n tend to infinity. And this means that the probability that we are looking at that is the probability that Sn over n belongs to the interval x plus eta converges to 1/2 as n goes to infinity. It converges to the difference between the distribution function phi at plus infinity minus its value at 0. Okay, so are we happy with that? Yes, we are very happy with that, because remember that the asymptotics we are looking at is simply taking the log of this quantity. So the log will go to minus log of 2 and plus 1 over n. So the 1 over n will completely destroy things, and we are happy at the end of the day. We get that lim inf over n of 1 over n, the log of the probability that Sn over n belongs to the interval x plus eta is lower bounded by minus psi star of x minus eta times lambda x. And since eta is arbitrary, you get that the limit is low bounded by minus psi star of x. And this achieves the proof is finished under the two extra assumptions that you have made. Now we have to relax these two assumptions. So first, we have to deal with the unbounded case. Still, we are at an ordinary point, x, but we relax the boundedness assumption. So to do that, we simply introduce bounded variables by a truncation procedure. I take some quantity m, which will be a parameter of control for the truncation. And we introduce variables x1m, xnm, which are IID variables with the same distribution mu sub n, with mu sub n of A, which is equal to the measure of A intersected with minus m plus m over the measure of minus m plus m. So of course, this is defined, well defined when n is large enough, in order to warrant that here you have something which is positive, which of course arrives when m is large enough. Now, we merely say that the probability that Sn over n belongs to x plus eta is larger than the probability of the same event, but assuming also that for all j, the variables xj r less than m. And this probability in turn is equal to the probability then the truncated variables belong to x plus eta times the measure of minus m plus m to the power n. And where Snm here is simply the sum of the xim variables. So now we can use the preceding result on the truncated variables. And this means that the limit of 1 over n log of the probability of Sn over n belongs to x plus eta is larger than minus psi star mu m of x plus the log of the measure of minus m. Which of course does not causes any problem because it goes to 0 as capital M tends to infinity. And this guy here is simply the log of the moment generating function of the distribution mu m. So at the end of the day, what you get is that this guy is larger than minus the sup. I express what is the dual of this log generating function. It is the sup over lambda of lambda x minus the log of minus m plus m of exponential of lambda z d mu of z plus the log of this probability here. And now, since m is arbitrary, you end up with the fact that it is greater than the infimum over m, the minus here, the sup over lambda of lambda x minus the log of the integral between minus m and plus m of exponential lambda z d mu of z. So are we happy? Yes, if we recover psi star of x. but this is not quite true, or this is true, but we have to work a little bit to show that it is true. What is simple is that we know that the inf of a soup is larger than the soup of inf. But for the converse inequality, for the other way around, we need to work. So we know that we have something, if we put the minus aside, we know that you have something which is in some sense larger than psi star of x, but we do not know that it is equal to psi star of x. We need an extra argument, and this extra argument is a min-max argument. That is, we have to use compacity. So again, you have to analyze things as functions of lambda and see what happens. So we start with functions Jm of lambda, which are the functions which appear in our inf soup, that is lambda x minus the log of the integral between minus m and plus m of an exponential of lambda z d mu of z. And we make sure that m is large enough so that the measure of x plus eta m is positive. And we do the same as before, as at the beginning of the proof, in fact. The same reasoning. And so we know that Jm of lambda is less than minus lambda eta minus log of the measure of x plus eta m, and which goes to minus infinity as lambda goes to plus infinity. And so this means that the set of lambda which are non-negative, such that Jm of lambda is greater than alpha, is compact, whatever alpha. This is a level set. Maybe empty, but it's compact. And therefore, if we choose alpha in a clever way, that is, we choose alpha which is equal to the quantity of interest, that is the infimum over n of the soup over lambda of lambda x minus log of the integral between minus m and m of exponential of lambda z d mu of z. D mu of z here. Then the compact, this level set, is non-empty by definition of alpha. And therefore, the family of sets, lambda non-negative, such that Gm of lambda is greater than alpha. This family is non-increasing with respect to the inclusion order, and it has a non-empty intersection. And this is a compacity argument. And now we are happy because we have the existence of some point lambda star belonging to the intersection of the level sets. And then psi star of x is for sure larger, since it is a supremum, it's for sure larger than the lambda star times x minus psi of lambda star. And this point lambda star is for sure, this value here is for sure, by definition of lambda star, the limit as m goes to infinity of Gm of lambda star, which is larger than alpha by definition of lambda star. And therefore, psi star of x is larger than alpha. And since we already knew that psi star of x is less than alpha, this implies that psi star of x is equal to alpha. And this achieves the proof in the unbounded case. Which is not completely trivial, because in the unbounded case, you don't know at all if the function psi is finite or not of a non-degenerate interval. You don't know anything about the integrability of the variable, so it's very complicated to make something neat. And the way you recover some neat proof is the way that I have shown you, that is with a limit. A limit procedure, triangulation procedure. Okay, so now we have to deal with possible degenerate cases. That is, what to do with a point x, which is extraordinary with respect to the measure. That is a point x for which there is no life for the measure after point x. So now what happens if whatever eta, the measure of x plus eta plus infinity is equal to 0. If it is true, of course, this means that the measure of the interval x plus infinity is also equal to 0. And so this means that the support of the measure mu is included in the interval minus x minus infinity x. And so it is for the convex hull of the support of the measure. So now, if you consider the soup of the convex hull of the support of the measure, it looks complicated, but it's not. The convex hull of the support of the measure, it's an interval. So this is just the right extremity of the interval, which is finite or infinite, but just the extremity of an interval. So you have two cases. Either x is larger than b, if possible. If b is plus infinity, this is impossible. But if b is finite, then it may happen that x is larger than b, or x is equal to b. These are the two different situations. So let's begin with the easiest one. If x is greater than b, this means that there is really no life for the measure after x. And so what we find on psi star is that it is equal to the soup of lambda x minus lambda by definition. So it is the soup of lambda x minus the log of the integral between minus infinity and b of exponential of lambda z d mu z. And it is greater than the soup over lambda of lambda times x minus b. So it is equal to plus infinity. So it's not surprising because this simply means that if point x is large enough and it's above, it's outside the support, then the tail is equal to 0. So yes, no problem. And now if x is equal to b, you have to analyze this carefully, which is finite, of course. This means that we merely lower bound the probability that Sn over n belongs to some interval b plus eta. We lower bound it by the probability that Sn over n is equal to x, which is equal to not xb. This is the same, but I have written b, so let's keep b, which is equal to the measure of point b to the power n. So 1 over n, the log of the probability that Sn over n belongs to b plus eta is larger than the log of the measure of point B. Okay, but in this case, if we compute psi star, then it's easy because psi lambda minus lambda b is equal to the log of the integral between minus infinity and b of exponential of lambda t minus b d mu of t. And you can use dominated convergence because here it goes to 0 if t is less than x, and it goes to 1 if t is equal to x. And so globally, this tends to this quantity here tends to the log of the measure of point B. And again, I have made a mistake here. This is not x, this is B. Okay, so what it means here is that the behavior of the function psi lambda minus lambda b, this means that it decreases to the log of the measure of b. And therefore, the maximum, the sup of lambda b minus psi lambda is equal to log of the measure of b. So psi star minus log. Psi star of b is simply minus the log of the measure of point b. And so the quantity that we had in the limit, which was minus log the mass of b for the measure mu, turns out to be the value of the rate function psi star at point b. So it's okay, and we are happy also in this case, and we have finished the proof in this case, and we have finished the proof of Kramers theorem, and we have also finished today's lecture. So we stop here.